So we're going to take a look at the area between two curves, sort of an extension of the area that we started with in the course, the area under a single function. This is the more general problem of finding the area that's bounded by two or more curves. So the area region bounded by the curves y equal f of x, and I've did an example of such a function here, this blue solid line here, and y equal g of x, which is this red dashed line here, and the vertical lines x equal a, which is this dashed line here, and x equal b, which is this dashed line here. Again, a being less than b, where both the functions f and g are continuous, right? No holes, gaps, jumps, vertical asymptotes, those sort of things. And of course, f of x being greater than or equal to g of x. Sometimes the book refers to f as being the top function and g of x being the bottom function over this interval. Then the area of this region, let me show you this region, right? It's trapped between the two functions f and g and between these two vertical lines. So if I shade in, goes up to this, stops at this vertical line. So just this region here, the area of this region is given by this integral. And it should make sense in one sense, because we can certainly break this definite integral up into what? The integral from a to b of just f of x dx minus the integral from a to b g of x dx, right? So I can use that by the property of definite integrals. But this integral here represents what? The area under this blue curve, right, all the way down to the x-axis here, which would be our green shaded in area plus everything under the g of x curve. Well, this integral, though, from a to b of g of x dx just represents the area under the dash g of x function and trapped between that and the x-axis. So if I take the total region and subtract this region, I'm going to get the shaded in region. So it makes sense from that perspective. I also want to do this because we're going to use this idea as we get into the looking at not just area but volume here shortly. Another way of thinking about this is if I were to estimate this area going way back to the beginning, right, estimate it with rectangles, we can partition the interval from a to b into n equally spaced subintervals. And let's suppose an arbitrary subinterval is right here, and if it's equally spaced, remember we have our delta x, which is the width, and then for some c sub I, right, or x sub I, or whatever you want to call it, it could be the left hand, right hand endpoint, midpoint, or any point in between. There's some c sub I in here, and from that I can obtain the value of the bottom function g of x and the value of the top function h of x, and those values will give me sort of the top and bottom of a rectangle. So let me show you that rectangle here. The width of the rectangle is delta x, right? And the height would be determined by the height up here at whatever this c sub I is. F of c sub I would tell us the height. So we would get the top of that rectangle, and then the bottom would be here. So these are straight line segments. Of course, the actual function's curved at the top and bottom, but this is a pretty good approximation. Then this red rectangle is approximating the area for this little thin strip delta x, right? And I can do that we'll have n equally spaced strips, and so for each strip we'll have a corresponding red rectangle. And so how would this look like when we were approximating? We would take the sum I equal 1 to n, and of course the width of each rectangle is delta x. What is the height? Well, what's the height of this? What is the height of this? Again, so if this value right here is what we're calling say x sub I, arbitrary value on that ith subinterval, then this is f of x sub I is the height, g of x sub I, right? It's the difference, f of x sub I minus g of x sub I. That's the height of our rectangle. F of x sub I would be the entire height up to from the x-axis up here. G of x sub I would be just this height, and so that our rectangle is the difference there. And so our Riemann sum would be the height of the rectangle is f of x sub I minus g of x sub I times our width delta x, right? So there's our approximation. If we add all n of these subintervals up, there would be the approximation for the area. Then what do we do to get a better approximation? Let n get bigger and bigger, more and more subintervals. Delta x approaches 0. And then what do? We take the limit as n goes to infinity. And what does this Riemann sum become? It becomes, by definition, the definite integral from a to b, right? F of x minus g of x dx, right? So it's another way of thinking about this. That's the same formula we just showed for the area bounded between these curves. Now the textbook's notation for this is again, the y top minus y bot for bottom, right? That's the idea. You want to make sure you subtract the top minus the bottom. If you get your subtraction mixed up, what's going to happen? You're going to get a negative quantity. These are area calculations. They will always be positive. So make sure you realize that. I know definite integrals can be negative, but in this section they should never be equal to a negative number because we're actually getting the area. And it doesn't matter if the graphs of f and g are above the x-axis like I've shown here or below. It doesn't even matter if they come below. That area trapped in between there is still a positive area. And what's going to happen is you're going to be subtracting negative numbers, so it's still going to work out and give you a positive quantity in there. This still works regardless if f and g are positive or negative. This will always give you a positive value if indeed you have correctly identified the top and bottom functions. So let's look at some examples here. Let's find the area of the region enclosed by the given curves in each case. So I think we got 3 or 4 of these to do. So I think it's very helpful to graph these functions, and so I've got a graph here we're gonna do. First function, y equals x minus 1. That curve is obviously a line, slope 1, and y-intercept negative 1. So the y-intercept is negative 1, slope is 1. Go up 1 over 1, up 1 over 1, and so on. We'll find the rest of the points on that line. That's sufficient to be able to sketch the line. Okay, so right there, that's the line y equals x minus 1. And then the other curve, what's that? That's going to be obviously what? A parabola. And since it's negative x squared, it's a parabola opening downward. Okay. In fact, it's really negative x squared and then adding 1. So it's the negative x squared is reflecting about the x-axis and then shifting up 1. You can think of it that way. Or we can just plot some points, right? When x is 0, y is equal to 1. When x is either negative 1 or positive 1, y is equal to 0. When x is plus or minus 2, 1 minus 4, y is negative 3. And so that's enough to sort of, we see the shape of our parabola opening downward. Let's just roughly sketch that. And then we're looking for the region enclosed by these given curves. That means our region has to be bounded by these curves. Okay, and the only region that is bounded by these curves is right here. Okay, so nothing over here. You say, well, it's bounded between these two curves, but it opens up, right? There's no boundary here. Same thing down here. There's no purple function below or anything to cut us off down here. So it has to be bounded by these functions. Okay, so there's the area we're looking for. And now from the graph you can clearly see sort of where our points of intersection are, but in general you should find points of intersection algebraically. A lot of times they're not necessarily nice whole numbers. How do you find points of intersections? Well, they're going to have the same y-coordinate, so if you equate these equations together, so in other words x minus 1 equaling what? 1 minus x squared. The y values of these two functions are equal when these quantities are equal. And then I just solve this equation for x. This is a quadratic equation. Set it equal to 0 by adding x squared plus x. Subtracting 1 from a negative 1 is negative 2. And then can I factor this over here? Sure, this factors. as what? Plus 2 minus 1, right? Product is negative 2, and outer and inner add up to positive 1x. And so clearly we see that the points of intersection are when x is negative 2 or 1. And of course, what is y? Well, I can plug in either one of these numbers into the original function. And what do I get? When x is negative 2, I get negative 2 minus 1 is negative 3. Right? When x is negative 2, I'm at negative 3. Same for here. 1 minus negative 2 squared, 1 minus 4 is negative 3. That's that point there. Of course, when x is equal to 1, 1 minus 1, I get 0. So that gives me my limits of integration here, right? Because the vertical lines we're integrating between are right here at negative 2 and right here at positive 1, right? So that's what we're going to integrate between. So our integral will be from negative 2 to positive 1. And what's our top function here? The green one. It's the top minus the bottom, right? So the top function is the parabola, 1 minus x squared, minus the bottom function, which is this case is the purple line, x minus 1. Right. So this is the book's y top and minus the y bottom. Okay. So it's important. If you get these subtracted in the wrong way, what's going to happen, when you change the order, what happens? It changes the sign, right? You would get, instead of getting the area, you would get negative 1 times the area. Okay, so let's evaluate this now. The integration is typically pretty easy here. And clean this up first before I integrate. So I've got 1 minus a negative 1. 1 plus 1 is 2. I got minus x squared and minus x. Right, distribute that negative through and combine like terms. So you should do that. You should combine like terms first. And now we can find the antiderivative of this function. What's the antiderivative of 2? That's 2x. What's the antiderivative of x squared? That's negative 1/3 x cubed. And the antiderivative of x is negative 1/2 x squared. There's our antiderivative. We evaluated at 1 and at negative 2. So at 1, what am I going to get? Replace x with 1. I'm just going to get 2 minus 1/3 minus 1/2. And then negative 2, 2 times negative 2 is negative 8. Sorry. Minor lapse of reasoning there. Negative 2 times 2 is negative 4. Negative 2 cubed is negative 8. That's maybe where I was thinking. Negative 8 times a negative 1/3 is positive 8/3. And then negative 2 squared is 4. Half of 4 is 2. Okay. And so now, I'm going to let you do the simplification here. And this comes out to be 9 halves, which is 4.5. Let you confirm that. So 9 halves or 4.5 is what we get there. So that is the area. And again, the graph that I've drawn is helpful because when you see this number 4.5, does that seem reasonable? Does it seem like there's about 4.5 squares in this region? That seems reasonable. If you got an answer like the area was 50 square, that's not going to be good, right? Something's wrong. So by drawing the picture and sort of eyeballing it, you can kind of get a feel for whether your answer seems reasonable or not sometimes. Okay. All right, let's look at another problem. This time we're looking at the functions x cubed minus 9x, which I've already graphed for you in the red here, and g of x, which is 7x, just a line of slope 7 passing through the origin. And let's find the points of intersection. You can probably see where they are already from the graph because it's drawn correctly. There's actually 3 points of intersection, right? So let's take a look at the points of intersection. So they're going to be the same when the outputs to the functions are equal, right? When f of x equals g of x. That's going to be when x cubed minus 9x equals 7x, right? When f of x equals g of x. So how do I solve a polynomial equation? Again, I set equal to 0. X cubed subtract 7x from negative 9x is negative 16x. and then factor. First I factor out the GCF of x, leaving x squared minus 16, and then x squared minus 16 factors as x plus 4 times x minus 4, right? Difference of squares. And so obviously x is going to be negative 4, 0, or positive 4. And you see those points of intersection. Now, in evaluating this, what is the region? Let's shade in the region. What is the region that we are going to be integrating here? It's trapped between these two curves. Well, there's actually two regions. There's this region here, and then there's this region here. Okay. So what do we have to do? Well, we have to actually set this up as, in this case, as two integrals if we're going to be doing it in what we call a vertically simple region. By the way, when we're talking about top and bottom functions, we talk about vertically simple regions, and that's indeed we have two vertically simple regions, not one. And the reason is, notice for this first region, we'll call this number 1, the top function is f and the bottom function is g. Whereas in the second region, that role is reversed, isn't it? The top function is now g, bottom function is f. What are our limits of integration again? Remember, we're at point of intersection negative 4, of course at 0, and then this point of intersection is x equal positive 4. So we've got two regions. So the area is going to be, first of all, this first region is the integral from negative 4 to 0. Top function is what? F of x, which is x cubed minus 9x, minus the bottom function, which in this case is the linear function g of x equals 7x. So this is number 1, plus then number 2, region number 2, its integral goes from 0 to 4. And this time the top is the g of x function, which is 7x, minus the bottom function, which is x cubed minus 9x. So there's the setup. You should simplify now to evaluate. So this is going to be from negative 4 to 0. And it's going to be what? X cubed minus 9x minus 7x minus 16x. And then from 0 to 4, 7x minus x cubed plus 9x. So 7x plus 9x is 16x minus x cubed. And you can see the difference between the two, right? When we just change the order, we subtract, we get opposites, right? This expression is the opposite of this expression. Okay. And so this says to evaluate with the function integrator on the calculator. So I'll do that this time. I mean, we could evaluate these if we wanted to. They're not too hard to evaluate. But I'll use the function integrator, if you remember, under math. Right there, FNINT. And I've got the function I'm integrating is x cubed minus 16x. The variable is x. Lower limit is negative 4. Upper limit is 0. And what do we get? 64. And if I do the other one, just edit this one, notice it's going to be 16x minus x cubed x, and we're going to go from 0 to 4. And hey, that's also 64. I wonder why that's the case. Well, if you look at the two regions, there's some symmetry going on here, and you can see why those two regions have the same area, 1 and 2. Be careful, it's not always perfectly symmetric problems, but the total then, 64 plus 64 is 128. Okay. So you can see we might have to split up the integral into more than one if the roles are changed where the top and bottom function are different. And you can imagine if you have a function going up and down a lot, you might have 2, 3, 4, 5 different regions you have to focus on. And so it's going to be important to be able to find algebraically these points of intersections and then set up making sure you get the top minus bottom correctly lined up. Let's do one more. Sometimes they just give the curves more than one curve, more than two curves rather. This one has 3 curves. Of course, y equal 1. Let's start there. That is, and we're just going to set up the integrals here. We're not going to evaluate them. So the first y equal 1, that's a horizontal line, right, at y equal 1. So let's draw that line. And then what do we have? We have y equals x squared. Well, we know that's a parabola opening upward at the origin, so we can do that. If x is 0, y is 0, 1 squared is 1, 2 squared is 4, negative 1 squared is positive 1, negative 2 squared is positive 4. And so we can sketch that parabola. Nice and smooth turning point there, right at the origin, minimum. And then what's this y equals x minus 4 squared? Well, really, if you think about it, this is the graph of y equals x squared. What? Shifted 4 units to the, since I've replaced x with x minus 4, this is a shift 4 units to the right. 4 units to the right. And you can see that because when x is equal to 4, 4 minus 4 is 0, I get 0, right? So x, let's do this in red, x is 4, y is 0. When x is 3, 3 minus 4 is negative 1, negative 1 squared is positive 1. Same with 5 minus 1 being 1, 1 squared is 1. At 2, 2 minus 4 is negative 2, negative 2 quantity squared is positive 4. And so you can see it's actually the graph of the x squared function just shifted over to the right 4 units. Okay, do you see the region that we need to find then that's bounded by all 3 of these functions? So be careful. This region here, it's bounded by the purple and the green function, but not the red function. And this region here is bounded by the red and the green function. It has to be bounded by all 3 curves, right? All 3 curves. And so the only region that's bounded by all 3 curves is this little region here. And it's kind of close to a triangle, but it's not quite a triangle because these are curves here. They're not line segments here. Okay, but do you see if we're doing this as a vertically simple region, we're going to have to break it up into 2 regions. Do you see why? So notice that from 1 to 2, so we right here at 2, we know that's that point of intersection. And I'm not going to solve algebraically for it, but you can see that's clearly the case, that x squared is equal to x minus 4 squared when x is 2, right? Plug in 2 for x, you get 2 squared is 4. Plug in 2 for x, 2 minus 4, negative 2 quantity squared is positive 4. So x equal 2 is that point of intersection right there. It's really at 2 comma 4. Sorry, I didn't quite draw that too good. Okay, but coming down then, for this region here, I'll call this region 1. The top function is the purple curve, which is y equals x squared. All right, let's make sure we know that this is y equal x squared. And the bottom function is y equal 1. And then in region 2, right, which goes from what, 2 to 3, region 2 here, the red graph is the top function. The red graph being, of course, y equal quantity x minus 4 squared. And so we have 2 integrals that we have to add together. The first, region 1, is the integral from what? From x equal 1 to x equal 2. And the top function is the purple function, which is x squared. The bottom function is this green line. We're not going all the way down to the y-axis, or x-axis rather. So we're going all the way down to y equal 1, so minus 1. Plus, region 2, the integral goes from what? From 2 to 3. Top function here is the red function, which is x minus 4 quantity squared minus the bottom function, which again is 1. Okay, and that's setting it up. I mean, that's sufficient. You could simplify by expanding and then subtracting the 1, combining like terms in here, but it was just a setup. So when it says set up the integrals, you don't have to evaluate them. I mean, you can use the function integrator if you wanted to check to make sure they're positive, but you can actually evaluate these. They're pretty simple to do. But the key is making sure you set up the integral correctly. Now, if we have regions like, what if we've had just two regions where the top and bottom changed roles. What if we have 3 or 4 or 5 of those? Sometimes it's better to, instead of thinking of things vertically, but to think of things as horizontally. And so here, just flip it around, here there's just sort of two functions horizontally that bound, right, this. And so we want to talk about integrating with respect to the y-axis. Let me do an illustration of that. Sometimes such a region that we can integrate this way is called horizontally simple. So let's find the area between the curves of this function x equal y squared minus 6 and y equal negative x. Now this is interesting because we don't have y expressed as a function of x, we have x as expressed as a function of y. So first of all, y equal negative x, we know how to graph that, right? That's a line of slope -1. The y-intercept is 0, so I go over 1, down 1, over 1, down 1, and so on. And so that's the, let's draw that curve. So this is y equal negative x. And then the other curve here, let's graph this. When this one, instead of plugging in x, I'm going to plug in y value. So when y is 0, 0 minus 6, x is negative 6. So y is 0, x is negative 6. So negative 6 comma 0. That's the point. What about when y is 1? 1 squared is 1 minus 6 is negative 5. So when y is 1, x is negative 5. What about when y is negative 1? Square negative 1, I get positive 1. 1 minus 6, and x is negative 5. Plug in a few more. When y is 2, 2 squared is 4, minus 6 is negative 2. So when y is 2, x is negative 2. When y is negative 2, same thing, right? Negative 2 squared is 4 minus 6. X is also negative 2. Plug in 3 for y. 3 squared minus 6. 9 minus 6 is 3. So when y is 3, x is 3. And then plug in negative 3. Square that, you get 9 minus 6, you get positive 3. So when y is negative 3, x is positive 3. And what do we have here basically? This, some of you know already, this is a parabola, but it's opening to the right because it's x equal y squared, and y squared coefficient is positive. So it's coming in, it's opening up to the right here. Okay, and so we see the region we're looking for here. Let's just shade that in. This is the region bounded between the two. Now, I could do this one the way we've been doing it, right, vertically, but it's a little challenging because right here, going from, let's just confirm the points of intersection, by the way. I mean, we could see them, but again, it's good practice. Find these points of intersection, and then we'll come back to that. This time I can create, set the x coordinates equal to one another. So in other words, when y is equal to negative x, that's the same thing as what? X being equal to negative y. So if x is negative y and x equals y squared minus 16, we've got y squared, sorry, minus 6. Y squared minus 6 is equal to negative y. So adding y to both sides gives me that, and this now factors. All right, and so y is what? Negative 3 and positive 2. And you can see that now at y equal negative 3, right, where we have that point of intersection there. And then up here, right at positive 2. Okay. That's the y coordinate. Of course, the x coordinate is 3, and we can find that by plugging in, right, y equal negative 3 into either side of this equation, and we'll get 9 minus 6 is 3. We get x is 3 there. So what would we have to do? Well, there's also, this point of intersection. We said when y is 2, x, of course, is going to be equal to what? When y is 2, x is going to be equal to negative 2, right? 2 squared is 4 minus 6, negative 2. X is negative 2. So at that point. And we could see if we're integrating vertically, we've got two regions where the top function, right, is different, right? Over here, the top function is the purple curve. Over here, it's the black curve. So I'm going to have to set up two integrals that way. However, if we think about it horizontally simple, then, going this way, we've got the region bounded between just two curves, the black curve here and the purple curve here. And that's what we're going to do. We're going to integrate that way. And the way we do that here is we're going to integrate from negative 3 right down here, negative 3 up to what? 2. We're integrating with respect to y, so y varies from negative 3 to 2. And we want to do the x function that is to the right minus the x function to the left. And I'm integrating now with respect to y, so notice my variable is dy. And why the right minus the left? Well, when we're talking about the real number line, the y-axis, right, goes up as we move up, right? And that's why the top minus the bottom. The top has a bigger value than the bottom function, right? Because we increase as we go up. But x-axis, where do we increase? Going to the right. So the further to the right you are, the more positive you are, the bigger you are than the value to the left. And so I can subtract, right, the right minus the left. Okay. Essentially what we're doing here, if we want to look at it, is we're partitioning the y-axis from negative 3 to positive 2, doing our rectangles, right, and integrating. And so it's with respect to this axis, which is the y-axis, and that's why we've got dy. And so what do we have for our x right function? What's the rightmost function? The rightmost function is this black one, right? It's to the right of this region here. And it's what? It's y equal negative x, or what? X equal what? Negative y. So that's negative y. That's our right function. What's our left function? It's this purple function, right? And that purple function, remember, was the line x equal y squared minus 6. So that's our leftmost function, right? It's to the left of the region. So this is going to be y squared minus 6. So our integral is from negative 3 to 2 of negative y. And I've got minus, be careful here, y squared minus 6. So I'll have to distribute that negative y through. And we get the integral from negative 3 to 2, negative y minus y squared, negative times negative plus 6. And this is pretty easy now to evaluate. One integral to do, the antiderivative of y is 1/2 y squared, so that's negative 1/2 y squared. The antiderivative of y squared is 1/3 y cubed, and the antiderivative of 6 is 6y. And I'm evaluating this at the upper limit of 2 and the lower limit of negative 3 and subtracting. So I'll let you grind out the work on that, and you should be getting 125/6 as your result. So that is an important thing to see, that we can simplify calculations, sometimes integrating with respect to the y-axis. Okay. All right, so I'm going to stop the video here. There's lots of examples that you want to work on, because there's lots of types of functions and arrangements we can make, but this is the basic idea behind finding the area bounded between two or more curves.